We've already talked about how to categorize matter into different categories, like pure substances or mixtures, and further divide pure substances into elements and compounds. And now we're going to talk about the different states that those pure substances may have. States of matter is one way of phrasing it, and the other word that is sometimes used is phases. So they are also known as the phases of matter interchangeably. All right, so there are three basic states of matter, and in a later lesson we will talk about a possible fourth state. But right now we're limiting ourselves to the three basic states: gas, liquid, and solid. Okay, so a gas is, in this case I'm showing a picture of a diatomic element, but it could be any element or any compound that is in the gas phase, and that has the characteristics that you see: individual units or atoms or molecules, and there's always space between them, except of course when they happen to collide with one another momentarily. They also expand to fill the entire container. So whatever container you have a gas in, it will expand until it fills that container. And further, they are easily compressible. You can squish the container and you will squish the gas. All right, so contrast that with liquids and solids, which are all considered condensed phases. They're more condensed. They don't take up the entire container necessarily. And so with liquids, the atoms or molecules are condensed, but they still flow. They still flow around. So you can think of these in terms of the phases of water as an example. We know gas phase water is water vapor. The little water molecules are traveling around in the container. Liquid water, it flows around. And then finally, solid is where the atoms or molecules stay essentially in place, and they just jiggle around. So they are fixed in some kind of array. Shown here is an ordered array, and they do move around, but they don't flow around each other. They mostly stay in place and wiggle. So you can think of this in terms of ice. The molecules in ice are fairly fixed. We don't see them jiggling, but they are jiggling. But they don't move around or flow like the liquid. So the three different phases of water are something we are all familiar with. But what we're not familiar with is that those three phases occur for all pure substances. We just don't usually see them in more than one phase. Sometimes we see them in two different phases, like we may have seen solid iron, and you may have seen a blacksmith melt iron. But for most things, we've only seen them in one phase. Now we can go between the phases, and we have specific terms for transitions between phases, which I will cover now. If you go from a liquid to a gas, there's a couple different things that could be going on. You could be boiling. Okay, when you boil water, it turns into the gas phase, or you may simply be evaporating. And those are not the same process, but they do result in going from a liquid to a gas. Now, if we go the opposite, if we go from the gas to the liquid, that's known as condensation. And it doesn't matter if this is water or another substance. Now, going between liquid and solid, if you go from a liquid to a solid, think in terms of putting your liquid water in the freezer, you are freezing it. And if you take your solid ice out of the freezer and let it turn to liquid, you are melting it. So those are the phrases going from liquid to solid and solid to liquid. Now, in some cases, you can go directly from a solid to a gas without going through the liquid phase. If you're familiar with using dry ice, that's an example of that. It's solid carbon dioxide, and it becomes gas phase carbon dioxide without ever being a liquid. That process is known as sublimation. And the opposite process, going directly from gas to solid, is deposition. Now, deposition is a very important term for for vacuum science. And in fact, sometimes vacuum scientists refer to deposition of a liquid. And of course, deposition is from gas to solid. What they mean when they talk about deposition of a liquid is they take the liquid, they first evaporate it, so they go up from liquid to gas, and then it gets deposited as a solid. Okay, I've used the term molecule here, which I haven't used much before, so I want to define what a molecule is. So a molecule is the smallest unit of a group of atoms that are bonded together. Okay, so that's similar to a compound, except that it doesn't have to be different elements. So for instance, so it can be an element, such as one of the diatomics, like H2, or it can be a compound, such as H2O, water. And another thing I want you to note from this page is that a change in state does not change the substance. So what do I mean by that? I mean, when you have water in the solid form, ice, it's H2O. When you have it in the liquid form, it's H2O. When you have it in the gas phase, it's still H2O. It doesn't come apart. The individual molecules stay together, so it does not change. Okay, so how do we know what state something's going to be in? Well, I'll give you a few guidelines. Okay, at normal room temperature, which is about 23 degrees C or about 72 degrees Fahrenheit, and normal room pressure, which is, depending on where you live, around 1 atmosphere, most metals are solids. In fact, all metals are solids except for mercury, which is Hg. Okay, so iron is a solid, sodium is a solid, copper is a solid, etc. They're all solids. So if you see a metal, you know it's going to be a solid unless it's mercury. Any compound with a metal in them are also solids. Okay, so for instance, NaCl. Sodium's a metal, so that's a solid. Copper nitrate. Copper's a metal, so that compound is a solid. So whenever you see a metal atom in a formula, that means that substance is a solid. Okay, the noble gases. Those are a certain group in the periodic table, and those are all gases. Okay, for example, helium, neon, argon, krypton, xenon, and radon are all gases. Now those are some general guidelines that'll cover some things, but for everything else, you're going to need to find a melting point or a boiling point, or both, to determine the state that it's in. Okay, so let's look at some examples. We'll start with water. Okay, so I put this dotted line to represent room temperature. And I'll do it in Celsius, 23 degrees C. That's room temp. And so we use the melting point and the boiling point to determine where room temperature falls in with the melting points and boiling points. Okay, so for water, the melting point is 0 degrees C. So we're going to put that down here. And that's the melting point for water, which means below 0, water's a solid. And above 0, water's a liquid, until, of course, you get up to the boiling point, which I'm going to put up here. and that's 100 degrees. That's the boiling point. So it'll stay liquid all the way from 0 up to 100, and then above 100 it'll be a gas. Okay, so since room temperature falls between the melting point and the boiling point, in fact I'll write MP and BP for melting point and boiling point. Since it's in between, that means it's a liquid at room temperature, which of course you know at room temperature is a liquid. But let's look at some other substances. Look at iodine. If you look up its melting point, you will find that the melting point is way up at 114. Okay, the boiling point would be even higher, so I'm not even going to bother mentioning the boiling point, because you can already see that if the melting point's up there and everything is a solid below its melting point, that it must be a solid at room temperature. Okay, because boiling point's always higher than melting point. So iodine is a solid. Okay, water is a liquid. Iodine is a solid. Let's look at another example. Sulfur dioxide, SO2. Okay, if you look up its melting point and boiling point, you'll find the boiling point is way down here, -10. These are all degrees C again. That's its boiling point. Okay, its melting point is way lower than that, so that's off our scale, which means that it is a liquid below -10, and it's a gas above -10, so it is a gas at room temperature. And for the final example, N2O5. Look up its boiling point and melting point, and you'll find that the melting point is 41 degrees, and the boiling point is just a little bit higher at 47 degrees. So BP, MP. So it's going to be a gas up here. In between, it's a liquid, and then below it's a solid, and room temperature is below that, so it will be a solid at room temperature. Okay, why don't you try some of these on your own? Use the guidelines that were provided and determine the state of each substance at normal room temperature and pressure. Now, some of them have data given for melting point and boiling point. The others you should be able to determine using the guidelines. Okay, the first substance, C3H8, which is actually propane, we have data, melting point and boiling point. What we have to do is determine where room temperature is compared to those numbers. Okay, and room temperature in degrees C is about 23. Okay, so 23 is higher than the boiling point. So you could draw a little chart, and it would be something like it is for SO2, where the boiling point is already below room temperature. Okay, the melting point's way below room temperature, the boiling point's below room temperature. So we'll say room temperature is above the boiling point, and therefore it's a gas. Aluminum oxide, it's a compound containing a metal. So we can just use the guideline that says that's got to be a solid. Neon, that's a noble gas. So it is a gas. CS2, carbon disulfide. Here's some melting point and boiling point data. Figure out where room temperature is. And on this one, it's above the melting point, below the boiling point. So room temperature is between, which means that it must be a liquid at room temperature. And finally, sodium. Sodium is a pure metal, so it's going to be a solid at room temperature. All right, one more try this using some of the boxes and representations of elements that we've had before. For these three boxes, show a mixture. For these three boxes, identify the state of the two elements in each box. And all of them are stated to have mixtures. All right, the first one, you can see two separate things. They're not bonded together. The shaded and unshaded are not attached to one another. So you have the solid ones. Those would be a liquid because they are condensed. They're not taking up the whole container. And they also are not ordered. So they're not a solid. And the same thing with the unfilled ones. That is also a liquid. Okay, in the second one, the shaded ones are taking up the entire volume. They're not condensed, which means they are a gas. And the unshaded ones, exactly the same thing. They're just spread out through the container, so they are also a gas. In the third one, the shaded ones are spread out through the container, whereas the unshaded ones are condensed at the bottom. They're not ordered, so, whoops. So they would be a liquid, and the shaded ones would be a gas.